This video is to understand how the lift well structure has been designed. To start with, first we should know the structural configuration of the lift structure, which is going to be modeled in STAAD for the analysis and design. These are the plan at various level for the lift well structure, and as we can see, you have this grid marking also. And say if I look my lift well structure from the left, I get this elevation, left side elevation. The lift well structure has been modeled in STAAD. So my first step will be to ascertain the geometric modeling, the properties of the member which has been defined in STAAD. So this is the lift well structure. So first what we'd like to do, we'd like to see the left part of the structure. This is the left side elevation of the structure. I would like to ascertain the dimensions. So this dimension is 2.23, 2.226, 2.226, 2.010, and we have 710 mm, 680 mm, and finally we have 1.2 meter. The column to column spacing should be 2.33 meter. So let us see here whether it's matching or not. So you can see it is 2.23, 2.226, 2.226, which is matching. Then we have 2.010 over here, 710, 680 and 1.2. So yeah, this is also matching. Finally, the center to center distance between this column is 2.33 meter. So the left side elevation part is matching. So this is the rear side elevation which we can see for this structure instead. This is the rear side elevation. So same over here, we had seen this dimension, these dimensions were matching. I would like to make sure that from here till here it is 2730 millimeter. So it is 2730 millimeter. Moreover, as we can see from here, these has been assigned member number 3, these horizontal member, and these bracings has been assigned member number 7. Would like to see in the drawing what is member number 3. Member number 3 is ISMC 125, and member number 7 is single angle section 75/75/6. We would like to verify whether this section property has been defined in STAAD or not. So we can see this is ISMC 75/75/6 defined for bracing members, and we have this ISMC 125 defined for the horizontal members. And if I look into the vertical members, the vertical member is being given member number 1, as you can see. So these are member number 1. So member number 1 should be 2 ISMC 250, that is channel section connected back to back. So we can see this is ISMC 250. So similarly, we can check for the other members also, and whatever properties which is being provided in the drawing, same thing is getting reflected in my steel structural members. Now this steel structural member is getting supported from the RCC wall, which is being supported by the raft slab. The thickness of the RCC wall should be 300 mm. So we would like to confirm whether the same input has been given here or not. Like here, if I select this plate thickness, the raft slab has been selected, and I can see the raft slab thickness is 350 mm. Now if I look into this, this is for RCC wall, as you can see it's been highlighted. This thickness should be 300 mm. So this is also matching with the dimension which has been provided, 350 mm and 300 mm thick. Would like to see the raft slab dimension. The raft slab is having plan dimension of 3.9 by 3.5. So same has to be here in my STAD. Let us see the raft slab. So you can see 3.9 and we can having 3.5 meter also. We can see that the dimensions defined in STAD is matching with the structural configuration of the lift well structure, and also the properties which is there in the drawing, same thing is present in my STAD model also. Now let us see the support which has been defined for our raft. If I click on support, we see here support 3 has been assigned, and it has been assigned with a plate mat with subgrade modulus of 2284 kN per meter square per meter. So how this value has come, we have the soil investigation report for Chowki railway station, and this has been considered. Like here the settlement calculation is 39.4 and the allowable bearing pressure has been defined as 9 ton per meter square. So if we do 90 divided by 0.0394, we get 2284. This is the subgrade modulus which has been defined. So the support has been defined, and this is how the lift well structure looks like. If I do the 3D rendering model, this is how the lift well structure looks like. Now we'll explore the loads that has been applied on the lift well structure. So first we would like to see the load which is going to act on the RCC wall and on my mat. So the parameters for the pressure distribution calculation which has been considered, like active earth pressure coefficient has been considered as 1 by 3. The density of soil is 18 kilonewton per meter cube. The wall height, as we had seen in the structural drawing, it was 1.65 meter. The surcharge load which is going to be considered is 10 kilonewton per meter square. So if we do the surcharge pressure, it comes out to be 3.33 kilonewton per meter square. Similarly, if we look into the lateral earth pressure which is going to act on the wall, if we do the calculation, if you see this calculation, it comes as 9.9 kilonewton per meter square, and it has been assumed as 10 kilonewton per meter square at the bottom of the wall. So if the surcharge pressure and the pressure due to the earth retained by the wall is combined at various level, the pressure distribution has been given. Like at top it should be 3.33, like at 0.4 meter depth it should be 5.7 and so on, and it should be at 1.65 meter it is 13.33 kilonewton per meter square. So if I open the STAD model and go with the load definition, under load definition, load case number 9, this tells us about earth pressure. We would like to see this pressure. Let me select only the walls. This dimension is 0.4. From here till here it is 0.8. From here till here it is 1.2, and from here till here it will be 1.65. So let us see here. You can see 3.33, 5.75, and the design document also we have 3.33, 5.7. Now from 0.4 to 0.8 it should be 5.7 to 8.18. So let us see here. So same thing as you can see, 5.75 to 8.18. Next, this load, it is 8.18 to 10.6, 8.18 to 10.6. Lastly, it should be 10.6 to 13.33. So 10.6 to 13.3. So this lateral arch pressure is getting reflected. So let us come to this pressure of 30 kilonewton per meter square, how actually it is coming. So if I look into this drawing, this projection of 400 mm, if we give the backfill, so this backfill is going to put certain weight on this projection. So that load has to be applied on this slab. So the density of soil is being considered as 18 kilonewton per meter cube, and depth of the backfill, as you can see, it's 1.6 meter. So pressure at that depth, the pressure which will be applied on the slab, it should be 30 kilonewton per meter square. So this load has to be applied on my raft slab. So let us see whether it's there or not. So if we look into this, so you can see it is having 30 kilonewton per meter square for the projection of 400. Last we will see this 36 kilonewton per meter square, how this has been applied on the structure. So these are the pit floor load which has been given, 39 kilonewton, 29 kilonewton, 26 kilonewton, which will be applied on the raft. So all these load has been summed up, and this has been applied on the floor area of 2.1 by 2.5. So if I divide this gives us a pressure of 36 kilonewton per meter square, and same load we can see has been applied on that area. So here we have seen the earth pressure load, the pit floor load which has been applied on the substructure. Now we'll look into the dead load and live load which has been considered for designing the lift well structure. So first we'll see dead load. So the self weight of the member has been assigned. Now we have this load of 1 kilonewton per meter which has been applied on all these members. Now these members are expected to carry the load of the claddings which is going to be supported on these members. The design document, as we can see, the cladding load 1 kilonewton per meter which has been applied on these members. Next, floor load of 2 kilonewton per meter square, that is the dead load of the sheeting, has been considered. So in the design document it's been mentioned dead load on roof, that is 2 kilonewton per meter square. So this load is also there in stat. So on this area the dead load is being considered as 1 kilonewton per meter square. Then there is some machine load which as per this drawing which has been specified. Say here, as we can see, we have P1, P2, P3. Now this load P1 is getting supported from this two beam. Similarly, this P2 load is getting supported on this two beams. P3 load is getting supported on this two beams. From the load data, P1 value is 43 kilonewton, P2 is 19.5 kilonewton, let us say 20 kilonewton, and P3 is 14 kilonewton, and this has also been there in the stand, that is total load of machine unit 43, 19.5 and 14 kilonewton. As we can see that this load is going to get divided into two beams. So 43 kilonewton, if I divide this by 2, it will be 21.5 kilonewton, and we see here this 21.5 kilonewton is being applied. Similarly, this load of 19.5, that is 20 kilonewton. When you consider it is 10 kilonewton, so this has been applied in the stack node, and same thing is 7. Okay. Now this 30 kilonewton load is coming, as you can see that there is a 3-ton capacity hooks which has to be provided at the top level. So we have to apply this 30 kilonewton load at this level. So these are the dead load which has been applied in the structure. Next, let us see the live load which has been considered. So the live load on this platform is considered as 5 kilonewton per meter square, which is given over here. Load on platform load, that is 5 kilonewton per meter square. Now live load on lift machine, that lift machine area, 10 kilonewton per meter square. As you can see, it's been over here. Now at roof also there is going to be some live load which is mentioned in the design document as 1 kilonewton per meter square, which is given over here. So as we can see, the dead load and live load has been applied at the respective location in the stack. Now coming to the wind load calculation has been done as per IS 875 part 2016. The basic wind speed is 39 meter per second, and the design wind pressure will come 0.6 Vz square. Now this design wind pressure has been calculated, and it has been applied on the column in X direction, in Z direction, again in X direction, and finally in Z direction. So this wind pressure has been converted as a UDL that has to be applied on these columns. Now there are various load combination which has been considered, which has been given over here for designing the structure and for the foundation design. So we can see these load combination has also been provided. Now the design command has also been provided to see whether the structural steel member passes for the design load which is going to come on the structure. The design has been done as per IS 800 2007, and if we analyze the structure, we see there is no error. And say if I want to know whether the steel structural member has failed or not, so that we can check by doing select the specification, all failed beam. So stat is saying that no beam has failed. It means that the structural property which has been assigned in this lift well structure for the load which has been considered is safe. Next, say if we want to know whether the base pressure on the raft slab is less than the safe bearing capacity of the soil. The safe bearing capacity of the soil is 90 kilonewton per meter square. I want to check whether it is passing or not. So you can do that. Okay. This you can see here is the raft slab, and here we can see the pressure contours, and this is the pressure contour, and we can clearly see for this load combination it is 75 kilonewton per meter square, which is coming because of the loads. And if I keep on changing the load combination, it is 70, you can see from here, and here this load combination is changing, 73, 74, so we can see for the service load combination the maximum base pressure what was coming is 75 kilonewton per meter square for this load combination, dead load, live load and earth pressure, which is less than 90 kilonewton per meter square. It means the foundation is safe against safe bearing capacity, the permissible settlement. If I want to design this slab, I would like to know the moment about x direction and y direction. Now to do that, I will consider the ultimate loads. Now for this load combination, that is 1.5 times dead load plus 1.5 times live load, the maximum moment which I am getting is 8.1 kilonewton meter. If I want to know the design moment, I can change my load combination, and here I can see I have 20.4. So this is changing. So I have this various load combination which is getting changed over here. So from here I can say that my design moment for designing the reinforcement about x direction, it is close to 21 kilonewton meter. Similarly, what we can do, we can find the design moment about y direction, and I can just have a look into what can be the design moment. Here you can see minus 21. So the maximum design moment is going to be 22.2, which is being governed by this load. And if I use these moment, and if I see this reinforcement which has been provided in this design document, has been mentioned. Yeah, design moment nearly equal to 20 and 20.5 respectively. And based on those movements, if you provide 10 dia bar and top and bottom, it is adequate. So this reinforcement is being provided in the raft slab, which is being shown over here, 10 at 150, both at top and bottom in both directions. This is adequate. Similarly, we can see the stress contour diagram and try to determine the design moment about x and y axis for this RCC wall. It is 18 and 22, and if you provide 10 die at 150 center to center both direction, so it is adequate, it is sufficient for this moment. So likewise, the check has been made. Till if there is any clarification which is required, you can always come back to us. Thank you.